Do you actually look at these videos?
I watched one because I missed one.
They are helpful? Okay.
I watched one.
In that case, we'll carry on. Even if just one or two of you are looking at it, that's
I gotta
fine.
give some comments so you feel supported.
Okay,
Up and coming YouTube.
so
Needs the subs.
we are going to continue our discussion of inductance this morning. We'll hopefully wrap up by the end of today, and then that leaves us 2 sessions next week to talk about unification of electricity and magnetism, Maxwell's equation, and the consequences thereof. So the sort of pulling together of the various threads next week I find to be a very kind of, I don't know, it's just a nice way to kind of unify what we've spent 3 months working on in this very elegant framework, and I hope you'll feel the same way this time next week. Okay, but in the meantime, before getting to work on the topics on the right, let me say a few words about this, since a couple of you asked me yesterday. So final exam schedule, I can't remember the date, I think it's towards the end of the exam period, maybe on the Thursday morning. 3-hour exam. For those of you who are 1601, very similar format, so very likely around 8 problems, plus or minus 1, depending on what I eventually write. About half of them will be on new material, since the second midterm, and the other half on earlier material. Okay, so fairly obvious rationale there. I will post at least one sample exam of my coursework this weekend. So again, all the usual stuff that you can be familiar with. So I've scheduled, I can't remember if I put this on the courseworks yet, but I certainly told you guys some time back for the timing of these. I'll put them on courseworks if they're not yet there, but there are a couple of so-called review sessions scheduled, and they are the week prior to the exam, during reading period. I guess I'm curious, and maybe this is not a reasonable question, but I'll ask it anyway. I'm curious to get your thoughts on what makes for an effective review. I've traditionally kind of done a kind of overview of the entire material, and in 3 hours, which is what we have available in each of these review sessions, one obviously cannot work through extensive numbers of problems. So the end purpose of the reviews tends to be me emphasizing those topics that I feel are important, and giving you some very mild hints about where to focus your preparation efforts. But I kind of feel it's not the most productive use of that time. So if any of you have any suggestions about what you've seen in a review context for a kind of sciencey type course, I'm happy to receive those suggestions. If you're shy and don't want to say anything now, send them via email. No.
I think something that would be good would be enumerating like problem types that we're expected to know. Like, for example, like we're doing like Gaussian like surfaces. Like technically the like formula works for like any Gaussian surface, so we only need to know the like standard geometries.
Yeah.
So I think just being like having a list of like knowing these kinds of problems so that we can practice them.
So that usually I do anyway, and I will certainly do so again. Yep. Anything else? Yeah.
Pretty helpful to go over the problems with the review exam.
All right. If any of you have any thoughts on this in the next few days, just send me a quick email. Figure this out maybe by middle of next week. Okay. So I'm going to start off by talking about generators. And I set the scene at the end of Tuesday's class. We're going to use our little model here to kind of see how this works. So just big picture comments. This is going to be a way of transforming, so to speak, mechanical energy into electrical energy, generating current. And you'll see very quickly that this is essentially the exact inverse of the motor scenario we looked at a couple of weeks back it's exactly that. It's kind of reversing cause and effect. So nice symmetry there. So let me immediately show you the two schematics of our little generator loop here. Again, same setup we had for a motor. Okay? So in the original case we were looking at, and I want you to look at the thing on the left here, we had a magnetic field here in red, and what we were doing with the motor was driving current around the loop, and then we figured out as a torque, this thing turns, and if we configure the connecting electrodes appropriately with a commutator, we can make this a continually rotating motor. So now what we're doing is we've still got a magnetic field, we're going to assume it's uniform, but what we're doing in this case is the cause, so to speak, is we're going to make this thing rotate, and in doing so we're going to see that it induces a current, and we can extract that current and do something useful with it. So, two sketches you've seen already pretty much before. So let me just talk about a little bit of the practicalities of this. So I just said that in the case of a generator, we want to make this coil, this loop, rotate, okay? And so the most common way of doing this is somehow to connect it to some external, let me call it turbine. Turbines being things that have, like blades, sort of thing you might see on a jet engine if you're walking past it, getting on an airplane. So it's got a bunch of blades, and by driving some fluid through the blades, just by the way the blades are angled, you can make something rotate. Okay, so that's typically how we would set up something like this to rotate. And of course, the primary instance of this is in large-scale power generation. And what's happening there is the turbines are being made to rotate typically by driving steam through them, or in some cases directly by driving some liquid, typically water, through them. And so in the case of steam, when you think of power generation, fossil fuel, historically sources of producing steam, you burn coal, you burn oil, you heat water, it produces steam, you drive steam through the turbine, this thing rotates. Same thing with nuclear power. In principle, you use the energy associated with nuclear fission, typically boil water, drive steam through the turbine. The end effect is all the same. And of course, if you're driving fluid directly, liquid directly, then you might actually be sending it through the turbine. Perhaps a little bit less common, but variations of that in terms of, for example, wave power generation of electricity. So the end result in terms of turning a turbine is pretty much universal. How you get there varies, of course, and then we're going to have this thing turn. Okay. So once we've got this thing turned, we've got the two units up there. One of them looking from, did I orient this like that? Looking from the side, and then the other view looking like this. And you see in red the assumed direction of uniform B field in this case. Okay, so that's the setup. So let's immediately jump in and see what we can say about induction effects using our Faraday law. All right, so this thing is rotating at constant angular velocity, omega, around the central axis. Same thing here. Omega is kind of having this rotate in this sense, counterclockwise. I'm going to say that the area of this loop is big A. We've been working with rectangular loops for simplicity, but we can easily carry it over. Turns out more generally it's pretty much an H-shaped loop. And then here, let me remind you, as always, we define the orientation of our plane, which the loop lies, by the direction of the normal perpendicular area vector. That's this arrow up here. So that's that. And then the angle of that with respect to some external B field is this. Okay, so in fact the way I've drawn this is actually looking like that. Okay, so, all right, let's proceed. Okay, so as the coil rotates, of course, the key feature here is that the flux that is passing through the coil, defined by its perimeter, varies. So it's this variation that's going to induce an EMF and therefore a current. So what can we say about the magnitude of the flux? Our usual definition, V B dot A, and again we've got a rectangular coil here, so I'm just taking the total area. So B times A times the cosine of theta. And what I'm going to do now is recast theta in terms of something that explicitly factors in the angular speed, rotation speed at which this thing is going. So, of course, just go back to our first semester rotational kinematics. I can describe the angle at which this thing is oriented at any point as simply the angular frequency times some elapsed time interval t. Okay, so this then would become b times a times cosine of omega t. Yeah.
What's the orientation of this diagram? The lower diagram?
What's the orientation?
What like view is that?
So that's this view.
Oh,
Okay.
okay.
Yep. Move this here. Okay, so now I've got this. So now I know my flux, and I'm going to apply Faraday lens. Just call it Faraday. So typical. What I can say is that E is minus d phi by dt. And I'm going to throw in a complication here, which is a minor detail, but let me just draw your attention to it. As you know, I amplify effects in induction if I have, or in motor when we're looking at the original application, I can amplify the effects by having many, many loops in my coil here. And so in this case, since we're going to be using this for generating current, a simple way to amplify sort of bang for the buck, so to speak, would be to make this an N loop coil. So I'm just going to throw this in here. But it's a very minor detail, okay? It's just an amplification effect by having a big N for loops. Yeah, Hanson.
What's the omega coming out of the in the second?
Okay. It's just the direction of rotation. So I'm trying to give correct vector descriptions in both of these. So here this is spinning around this axis, and as such, as with any rotation, our unique unambiguous vector that defines this is pointing to the right. And in this case, this is rotating counterclockwise, and again, same right-hand rule convention. My omega vector, therefore, is pointing towards it. Okay? So a lot of right-hand rule stuff going on here. All right, so I've thrown in an N loop coil to give me more bang for the buck. And all I'm going to do now is differentiate this. And what I get out of this, again, N is optional, but let's kind of throw it in there to show us how to maximize what we can get out of this. I get this. And okay, sign's not so interesting here, but let me just pull out this minus sign and this minus sign. And this tells me now that I get N times B times A times omega times the sine of omega t. So, very quick, simple first derivation of what the EMF around this loop looks like as this thing spins around. Let's look at the parameters as usual, see if it makes some sort of physical intuitive sense. So the most interesting stuff is what's happening on the left side. This, of course, is just a sinusoidal variation with time. We get more EMF if I have many loops. Depends on the strength of the magnetic field, depends on the cross-sectional area of the loop, and it depends on the rotation frequency. Okay? So rotation frequency is key here. If I want to get a larger EMF, I want this thing to spin faster. Okay, so that's the EMF. Let me just talk about current briefly, and then we'll say something about how we can maybe do something interesting with this. So this is now connected to an external circuit, of course. and that external circuit has some resistance. And if that's the case, I can simply say that the current, I should have put an explicit T in here, because it has an explicit time dependence. So the current now is just E over T, E, ET over R. This just becomes N A omega sine omega T over R. Okay, so that's the current coming out of our spinning loop. Okay, so you know the answer to the following question, but let me just see if you've woken up. This gives us intrinsically alternating current. Okay, that's very practical, very useful for certain things. You will be noticing at this point that we're going to skip chapter 31 from our textbook, which is specifically devoted to alternating current. Lots of super useful things there, super interesting things, but we don't have time. It's more of a sort of perhaps applied/engineering topic also. So this gives us an intrinsic alternating current out of this thing. Fine for some purposes, but not so great for others. So how can I modify that intrinsically alternating current output? First off, to make it only flow in one direction. Even if I can do that in the way that you know the answer to, if I do it, I can get a current that flows only in one direction, but it isn't a smooth, constant current, which is to say it doesn't have the same value always. And the second part of the question is, how might you cleverly modify how this simple generator is built to sort of smooth out that time-dependent current when it's in one direction only? Okay, that was a very long question. So, how do I get this going from alternating current, where the current is going back and forwards, depending on the angular frequency? That's the first question, and then if I've done that, how do I smooth out the intrinsic sort of sinusoidal behavior in a clever way to get a more smooth one-directional current? Delphine?
I don't know if this would work, but could you like flip the magnetic field like regularly and then like
You
counteract
could. Sure. A little bit practically cumbersome, but yeah, that's certainly one way to do it. Looks like you maybe, nope, it was just this. Okay, yeah.
Would connecting a diode help?
And certainly connecting a diode will do it for you, but I want you to come up with a way, again, you already know the answer, that actually is even further upstream of that, and has to do with simply how I extract the current from this. Yeah. Okay, way too complicated. So, I mean, not to say it's not correct, but remember what we talked about 2 weeks ago, maybe, when we had our motor, we were driving a current around the loop. And what we saw in that case is, if I just set it up with the connections always made the same way, this thing alternates, it goes back and forward. So it rotates half a cycle, comes back, rotates half a cycle, comes back. How do we solve that problem? Yeah. We flip the direction of the current. And the way we did that was just have electrodes cleverly configured so that every pi rotation, the connection point of the electrodes flips. So we're going to do the exact same thing here. In this case, we're extracting the current rather than inputting it. But if I have the exact same setup, the so-called split ring commutator, then as this thing rotates, once it gets to that critical point, the sense of the electrode contacts is flipped, and so we get it coming out the same way. So, fine, let's say I've gone from this is my intrinsic output from the generator by making use of a split ring commutator, and I get it looking like this. Okay, but it's still not at all smooth, even though it's now one directional. How might I cleverly, again, something intrinsic to the design of this thing, how might I cleverly try and smooth this out in some way? Just an interesting design engineering question.
Can't remember exactly, but I think it's the resistor and the capacitor. And so like the capacitor charges up until it gets to the peak, and then it discharges really, really slowly. That smooths it out a little.
Okay, so number of you are inclined to think of things sort of immediately downstream once I have the current coming out of this thing. Even more simply, is there a way I could adapt this design to get the same end result without having to do anything with, let's say, electrical devices? Yeah.
You can maybe vary the angle as you start to switch direction, you can slow it down before you switch.
Okay, sounds really complicated, but I can see where you're heading. That would mean having a continually changing turbine speed and some hard to, not necessarily hard, but not straightforward way to apply. Yeah, go ahead, Kate.
Multiple rings.
Okay, I want to be a bit more specific.
This one's varying it that way because of its specific angle to the field. So if we have multiple ones that all have different angles to the fields, then they'll all vary in that path and then cancel each other out in terms of their
Okay, yes. So that's exactly what's done. So in practical generators, I don't just have one plane that has a loop in it. I have a complete sort of, I don't know what that thing's called. It's like a fan arrangement of multiple loops that are just mildly offset by a small angle offset with respect to each other. And so if you have that, and you completely fill the entire circle here, so to speak, and then add all of the outputs from each of these, you essentially are having multiple ones of these that are slightly out of phase with each other. Okay? So again, this both gets you more bang for the buck. You're getting more current because you've got more loops. But it's also smoothing them because the output from each is offset by a small phase difference to the other. And eventually this starts to look something like this. Okay? So that's typically what's done in practical power generation. Yeah?
What does that inverse switching connectors that work?
Are
Are they all connected separately?
They're all connected separately. Yeah. I mean, it's engineering-wise a little bit tricky, but actually not too bad. And you can't, there's a limit to how many of these you can have, so you're always going to end up with a little bit of ripple here. But it works pretty well. And I think in your textbook, if you open it up in this chapter, you'll see a photograph of one of these what are they called? I forget. Anyway, it doesn't matter. Okay, so, good. That's the basics that we need to know about a generator. Let me just say something finally about power associated with this. So this goes back a ways. You'll remember from a few weeks ago, we can define the power in some circuit as being the product of the EMF and the current. And if I take this and throw in the appropriate parameters, so what did I have? The sine of omega t, and then over here I've got NBA omega sine of omega t over r, and so this just becomes NBA omega squared sine squared of omega t over r. Okay, so that's the instantaneous power. I keep forgetting to put this exclusively as a function of time. What I maybe am more interested in is what is the average power of this thing, okay? Just out over the sinusoidal behavior, and I figure out the average. Okay, how many of you can remember what the average of a sine squared function is over an integer number of sine waves? Yes?
1 over square root 2 or something?
Sine squared function. On the right track? 1/2. Okay. So the average is just
Makes sense.
omega squared over 2r.
Oh, I was thinking of the root mean square.
I know.
Yeah.
Okay. All right. So very simple, really derivation here, and some useful parameters. Of course, this is maybe the most useful one, and we see the expected dependence on the parameters in our system. So fairly straightforward. Pause and ask for any further questions. Okay. All right, so let's move on and talk about inductance and inductors. I'm going to use some slightly vague statements to motivate what we're about to explore. So remember a few weeks back when we introduced capacitors and capacitance. So what were they all about? First off, they're devices that, in the case of a capacitor, enable us to store energy in an electric field. Okay? And if you think about our standard capacitor schematic, it's storing energy in the electric field between plates of a charged capacitor. So energy storage is one key use of a capacitor. The second sort of corollary, or the second effect that we learned capacitors can be useful for, is if we combine them with some resistive element in a circuit, then we get some intrinsic time dependence to things like charge, current, potential difference. So inductors are very much analogous roles, but instead of worrying about electric fields, we're going to be worrying about magnetic fields. Okay? So inductors will serve again as energy storage devices, but now energy is stored in a magnetic field in an inductor. And our sort of baseline device here, because in some sense it's the simplest one to work with, is a long solenoid. Okay, so just a coil of wire, helix if you will, and that's going to be our default configuration for an inductor. We store energy in the B field in the center of the inductor, and it turns out, as you see on the chalkboard here, we can also see that there are time-dependent effects associated with inductors and resistors in a circuit. I'm just going to hide that for now, since I don't want you to be too distracted by it while we talk about some of the introductory phenomena associated with inductors. So it's not an exact parallel, but it's close. And so first off, you might recall for capacitors, with our parallel plate devices, what we kind of relied on was the fact that an electric field and the associated electric potential across the plates of a capacitor, proportional to the amount of charge that's on the capacitor plates. And now for inductors, again, this is not an exact parallel because the constant of proportionality kind of kicks in the inverse sense. But what we're going to make use of is the fact that the magnetic flux in some to be defined area is proportional to current. Okay? Now, no big surprise there. We know that current induces a magnetic field, so since that falls in directly from magnetic flux, we know this is true. Now, what we're going to basically do is make use of this and throw in a essentially a constant of proportionality. And so we're going to in fact define this as the basis of inductance. So we're going to say that phi B equals L times I. Okay?